In the previous lecture, we talked about the forward propagation. In this video, we will discuss back propagation. So forward propagation means that you started from input layer and reached at the output layer. Since the weights are not optimized, so we need an optimized weights. For that, what we do, we move back from output to the input neurons. And we do this procedure again and again, so on. So it is very important part of artificial neural network and machine learning. The back propagation ensures that we have the weights W1 and so on, all the weights are well optimized. When this optimization has been completed, then we can use that weights for our test data. So this was the image that we draw in our previous lecture. Now we move forward and think about the back propagation. So the topic is the back propagation. If you are currently uncomfortable with these images and the weights and anything, just wait for the examples that will come in the future videos. So how we draw a back propagation, or how we move from output to the input. So first, we try to understand that for back propagation for neurons. For neuron. From this idea, for a single neuron, from a single neuron, we can go back and talk about the matrices form. So let me just draw an image for you. Suppose we have input data XA and input data XB. Then we have some weights, maybe suppose we have weights WA and weights WB. So you know that we need to write E as a form of XA WA plus XB WB. That's it. And the next step, what we do, we apply activation function. There is still no output over here. Until here, we don't have any output. The output of this result will be f of E. F of E. F is activation function, which we can call it y hat. So it means that y hat is a solution of artificial neural network. And we will compare this with the exact solution. And we know the exact solution initially. First of all, let me just define f dash E. F dash E is defined as what we want to optimize. First, the question is what we want to optimize. We want to optimize these weights. If these are optimized enough, optimized mean ideal value, which gives us the correct answer, this correct answer. So what we do, as I explained earlier, first we move from input to the output, then we move from output to the input, then again we optimize W, so on. So how this optimization will be done, we will talk about that now. F dash E, we take a derivative of our output. Remember that this is the output of two input neurons. This is a very simplistic model. As you know that from this image, this is a complex thing. So currently we are just talking about these two inputs and only one this neuron. This will be repeated for this neuron and this neuron in the hidden layer and many other neurons that we decided in the beginning for any problem. So partial y hat by partial e. That's how we define f dash. Why we want to take a derivative of y hat with respect to e? The reason is e is the linear combination of XA, XB, and WA and WB. And E contains our target, which is WA and WB. This is the target that we want to achieve. So first, we need to take a derivative of y hat with respect to E. Then we will take a derivative of E with respect to WA and with respect to WB. So we may write partial y hat by partial WA will be equal to partial by partial WA XA WA plus XB WB. We take a derivative with respect to WA, all others are constant, so we get X of A over here. Again, we differentiate y hat with respect to WB. Why we are doing that? Actually, we need to apply the chain rule. And in the chain rule, we will get these derivatives in our calculation. So first we need to find the derivative with respect to all the weights. Partial by partial WB, that will be equal to XA WA XB WB, and that will be XB. Okay. This was what we required for our future calculations. So we defined f dash, which is just a derivative of y hat with respect to E. Then we defined y hat with respect to WA and with respect to WB. Okay. Assume that at this stage we have an exact solution. Y, which is our exact solution, or it is a known solution or known value. And we want to compare y hat with y. So the y is our known value. So we want to find a difference between y, which is known value, and with y hat, which is obtained from artificial neural network. How we find that y hat that we obtained has a reasonable solution? We need to take a difference of these two, which is called an error. So the error that we want to measure is E is equal to y minus y hat. This is called an absolute error. When we have exact minus y hat, which is a machine learning answer. Since we need to find a derivative of this error with respect to some values that I will talk about that, and also we want a positive number. One option is to take a mod. Another option is to take a square. This square will make this difference a positive value. Suppose if y is 2 and y hat is 2.1. So in this case, you will get negative answer. So what we do, we take a square of that value. Now the problem is we have to make this error as small as possible. So what we do, what we learn from the calculus, we learn that if we differentiate this E with respect to some unknown, we differentiate that, then we can optimize the value of y hat since we want to find a best fit with y. In that case, when we differentiate that, you will get 2 y minus y hat. Now we don't want this 2 in our answer. It is just a scaling. So one option is how to remove this 2 from here. So what we do, we introduce 1 by 2 over here as well. This is just an error. Okay. So first we squared the difference between exact value and the machine learning answer. Then we added 1 by 2 so that when I differentiate E, this 2 and the another 2 in the denominator will be cancelled out. So we differentiate partial E by partial WA. That will be equal to minus. Now what we are doing, we are optimizing the error. We want to reduce the error, and optimization problem, always remember that you need to take a you need to take a derivative. So we have partial y hat by partial WA. Okay. Since E we have we differentiated E with respect to WA, so y hat actually contains, y hat is also a function of WA, but from the chain rule, we have minus y hat, partial y hat by partial E, and partial E by partial WA. That's why we needed a chain rule over here. Since, I repeat again, we want to take a derivative of this output with respect to WA, and WA is over here, but reaching WA is not easy. First you have to take a derivative of y hat with respect to E, then with respect to WA. That's why we used chain rule over here, and that is the reason that we introduced some differentiation before. Okay, so finally partial E by partial WA becomes delta, and we call it xi. What is delta over here? Maybe delta and partial E by partial WA, W, and this partial E by partial WA is xi. We are calling this xi, and this value over here is the E. I'm sorry, it is delta. This is the delta. Okay. Now we do the same. We differentiate now. We differentiate the error with respect to WB. The reason is E is a function of, not only a function of WA, but it is also a function of WB. So we need to optimize these two values. So this becomes minus y hat partial y hat by partial b, that will be equal to minus y hat partial y hat by partial e by partial wb. That is what we required for the derivative of e with respect to wb. Again, we call one term over here, which is delta, which is y minus y hat, and what was y dash e? It was f dash e partial e by partial wb, and we call that actually w, and then we put that value into the above equation. Partial e by partial wb is equal to w f dash, which is partial e by partial wb, and that will be equal to delta, and we are calling partial e by partial wb with xj. Okay, that's what we have done until now. We just differentiated the error. So how the WA will be optimized? Our aim is to optimize this WA. How this will be optimized? This will be optimized since we needed a new value. This is a new value. This WA is the old value. Now we have to add something over here. Suppose partial E by partial WA is the derivative of error with respect to WA. The direction of partial E by partial WA is the maximum value. We know that from calculus 3, when we differentiate f with respect to x, it shows the maximum rate of change. Maximum rate of change. If you want to minimize a rate of change, you need to multiply this with minus. This will give you the minimum rate of change. So it means that we add the old value, which is old, although these two look similar, but this is the old value. So what we do, we add an old value in the minimum value, so we need to add minus over here. So we add minus over here. since we get the minimum value WA. You want to minimize WA and WB. Now the problem is you cannot take one step. You cannot take one step towards the minimization. For example, if you have somewhere a minimize problem, you cannot reach over there in one step. What you do, you will reach in another point, then you will reach this point, so on. So you need different steps, small steps. So it means that we add some parameter over here, and that parameter is called the learning rate. This value is very small since to reach towards the minimum point, you need to iterate many times. So that's how the WA is updated. You need to update the value of WB as well, since these are the weights and these contributes in the linear combination. So what we do, we consider WB the old value. Again, the derivative of error term with respect to WB. Since we want to add a minimized term over here, so I take a negative of that value, and I also introduce the learning rate. Alpha is just a number which actually modify, it is also called modification rate of weights. It is called learning rate. It is a real number which shows that the modification rate of weights during training. So this was all about the back propagation only for one input, two inputs, but one input layer, and there is only one output. That's what we discussed over here. So we reached at this stage. So when you probably read some paper on machine learning, they talk about this optimization in the back propagation. They also talk about the alpha, and alpha is basically the learning rate. It is a learning rate. In the next video, I will talk about output, back propagation from output to hidden layer. Thank you for watching.